Good morning, everyone. Uh, Today we are going to discuss about Cayley-Hamilton theorem and its verification and find inverse and power of a matrix by Cayley-Hamilton theorem. This is discussed in our today's class. Here we have the statement Cayley-Hamilton theorem is stated as every square matrix satisfies its own characteristic equation or its characteristic equation. That is called the statement of Cayley-Hamilton theorem. Unfortunately, the proof of this Cayley-Hamilton theorem is not included in your syllabus because this is a engineering is an application oriented. That's why we need to solve the problems and apply the concept in engineering field. That's why Cayley-Hamilton theorem proof is not included in our syllabus. So here every square matrix satisfies. That means that in place of the characteristic equation, in place of lambda, we have to substitute capital A, the matrix square matrix. Then we get 0 or other way, or another way. The characteristic equation of every square matrix satisfied by the own. That means that every square matrix satisfies its own characteristic equation. For this, now we want to solve some of the problems by using Cayley-Hamilton theorem. Verify Cayley-Hamilton theorem for A equal to 3, 0, 0, 5, 4, 0, 3, 6, 0, 3, 6, 1, and hence find A inverse. A inverse from the Cayley-Hamilton theorem, not from the adjoint method or any another method. From this Cayley-Hamilton theorem, we have to find the inverse of this matrix, and then we have to show that or verify that the Cayley-Hamilton theorem is verified for this given square matrix. Now let us consider this given square matrix capital A equal to 3, 0, 0, 5, 4, 0, 3, 6, 1. This is an upper triangular matrix. Now we want to find the characteristic equation of, first of all, we want to find the characteristic equation of this square matrix. The characteristic equation of this square matrix capital A is determinant of A minus lambda I equal to 0. Substituting this value in this matrix, we get 3 minus determinant of 3 by 3 determinant of 3 minus lambda 0, 0, 5, 4 minus lambda 0, 3, 6, 1 minus lambda equal to 0. If you expanding this determinant 3 by 3 determinant by using row 1, we get 3 minus lambda into 4 minus lambda into 1 minus lambda. Remaining all values becomes 0. That means that 3 minus lambda into 4 minus lambda into 1 minus lambda equal to 0. Now expanding this values, we get 1 minus lambda into. There is no need to find the eigenvalues and eigenvectors in this case. We have to verify whether the given equation is satisfied by, whether the characteristic equation is satisfied by the given square matrix or not. After that, we have to find the inverse of a matrix. This is the only the way. So for this, we have to find the characteristic equation first. That is 1 minus lambda into 3 minus lambda into 4 minus lambda. 3 minus lambda into 4 minus lambda is 12 minus 7 lambda plus lambda square into 0 equal to 0. That is, now we want to multiply this equation with 1 minus lambda, we get 12 minus 7 lambda plus lambda square minus 12 lambda plus 7 lambda square minus lambda cube equal to 0. That means that minus lambda cube plus 8 lambda square minus 19 lambda plus 12 equal to 0. Now multiplying with minus 1, we get lambda cube minus 8 lambda plus 8 lambda square plus 19 lambda minus 12 equal to 0, treating that as equation 1. Now we want to verify whether the given equation or the characteristic equation of the given square matrix is satisfied by the given square matrix or not. For this, we want to find we want to check whether the given equation is satisfies the correct characteristic equation or not. For this, by Cayley-Hamilton theorem, the square matrix capital A satisfies the characteristic equation mentioned in equation 1. Now we want to show that A cube, in place of lambda, we have to substitute capital A, that is A cube minus 88A square plus 19A minus 12I equal to 0, because I is an identity matrix, there is no change in the value. So if this being a 0 matrix, then the Cayley-Hamilton theorem is verified. After that, we have to find the inverse of a square matrix. Now let us find here, if you satisfy this equation, we have to find the value of A square. Already we have A square, and then A cube. Then substituting those values in this equation, we get either 0 or any whatever. We have to check it. Let capital A equal to 3, 0, 0, 5, 4, 0, 3, 6, 1. Then A square equal to A into A, that is 3, 0, 0, 5, 4, 0, 3, 6, 1, 3, 0, 0, 5, 4, 0, 3, 6, 1. Now multiplying these two matrices, we get 3 into 3, 9 plus 0, 0, that is 9. Next 3 into 0, 0 into 16, 0 into 30, that is also 0. Next 3 into 0, 0 into 0 plus 0 into 1, that is also 0. Those are the values of first row. Next, now multiplying second row of first matrix with all the columns of the second matrix, we get 3 5s are 15, 4 5s are 20, 20 plus 15 equal to 35, 35 plus 0, that is 35 only. Next 5 into 0, 0, 4 into 4, 16, 0 into 0 into 6, that is also 0, so 16 is itself. Now 5 into 0 plus 4 into 0 plus 0 into 1, that is also 0. Next, by using third row, we have to multiplying all the columns of the second matrix. 3 3s are 9, 9 plus 30 plus 3, 9 plus 30 plus 3, 42. 3 zeros are 0, 6 4s are 24, 1 6 are 6, 24 plus 6, 30. Next 3 into 0, 6 into 0 plus 1 into 1, that is 1. So this is A square. Next, we have to find the value of A cube. A cube is nothing but A into A square. A is already known to you, that is 3 0 0, 5 4 0, 3 6 1. Substituting this A square value, that is 9 0 0, 35 16 0, 42 31. 3 9s are 27. Remaining values 35 into 0, 42 into 0, 0. That is nothing but 27. Next, from second row column, 3 into 0, 0, 0 into 16, 0, 0 into 30 is also 0. Next, 3 into 0, 0, 0 into 0, 0, 0 into 1 is also 0. So these 27, 0, 0 are the row values of A cube. Next, we want to multiplying second row with all the columns of the second matrix A square. That is 9 5s are 45. Next, 13 4 35, 4 into 35. Those sum is nothing but 185. Next, 5 zeros are 0. 16 4s are 64. 0 into 30 is also 0. That is nothing but 64 only. Next, 5 into 0, 4 into 0, 0 into 1, that is also 0. Next, multiplying third row with all the columns, we get 3 9s are 27, 6 35s are the value, and 1 into 42, then we get 279 is the value. Next, 3 into 0, 6 into 64, 1 into 30. That is nothing but 126. Next, multiplying third row with the third column of the second matrix, 3 into 0, 6 into 0, 1 plus 1 into 1, that is 1. So this is a cube, 27, 0, 0, 185, 64, 0, 279, 126, 0, 1. This is the a cube. Now we want to substitute these values in a cube minus 8a square plus 19a minus 12i. After simplifying those values, we have to get either zero matrix or not. We have to check it once. A cube minus 8a square plus 9a minus 12i equal to a cube minus 8 into a square plus 19 into a minus 12 into I. I is nothing but a 3 by 3 identity matrix. Now 27 minus 9 8s are the 72. 3 13 19 3s are the 27 57 minus 12. So that is becomes 0. In the same way, 0 minus 0, 0 minus 0, 0 minus 0, that is also 0. Next, third element is also 0. Next, 185 minus 8 into 35 plus 19 into 5 minus 12 into 0, that is also 0. Next, 64 minus 8 into 16 plus 19 into 4 minus 12 into 1, that is also 0. Next, 0 minus 0 minus plus 0 minus 0 is also 0. Next, 279 minus 8 into 42 plus 19 into 3 minus 12 into 0, that is also 0. That is because that becomes 279 in negative value. Then we get this value, right? Now 126 minus 8 into 30 plus 19 into 6 plus 0 into 12, that is also 0. Next, in the same way, 1 minus 8 into 1 plus 19 into 1 minus 12 into 1, that is also becomes 0. So this is a 0 matrix of order 3. Then this matrix a cube minus 8a square plus 19a minus 12i equal to a null matrix. Hence, the given matrix is satisfies the characteristic equation. The Cayley-Hamilton theorem is verified. Cayley-Hamilton theorem is verified, and then we have to take this value, a cube minus 8a square plus 19 minus 12i, 19a minus 12i equal to a null matrix can be treating as equation 2. Because we want to find, and one more thing in here is A inverse. For this, we want to multiply both sides of equation 2 with the A inverse. We get A inverse into a cube minus 8a square plus 19a minus 12 into I equal to 0. Now multiplying a square a cube into a inverse, that means that a inverse into a square minus 8 into a inverse into a plus 19 into a inverse into a minus 12 into I into a inverse equal to 0. That is nothing but a square minus a inverse into a is nothing but I into a square is I a square minus 8 into a plus 19i minus 12 into a inverse equal to 0. That means that a 0 matrix. Now we want to write down a inverse from this reduced equation in terms of a square matrix. A inverse equal to a square minus 8a plus 19, 12 into a inverse equal to a square minus 8a plus 19i. A inverse equal to 1 by 12 into a square minus 8a plus 19i. Now substituting a square value minus 8a and 19i value in this equation, then only we get the value of a inverse. That is nothing but A inverse equal to 1 by 12 into A square, that is 9, 0, 0, 35, 16, 0, 42, 31 minus 8 into A. 8 into 3, 0, 0, 5 into 5, 4, 0, 3, 6, 1 plus 19 into identity matrix of 3 by 3. That is 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, find the values and dividing with the 12, we get 9 minus 24 plus 19. 9 plus 19, 28 minus 24, that is 4 by 12. That is nothing but 1 by 3. Next, 0 minus 0 minus 0 by 12, that is 0 by 12, 0 itself. Next, in the same way, 0 minus 0, 0 by 12, that is also 0. That is the value of A inverse of first row. That is nothing. Next, we want to find the second row of A inverse. That is 35 minus 40. 35 minus 40 minus 5. 0 minus 5 by 12. Next, 16 minus 32. 16 minus 32 minus 16 plus 19. Minus 16 plus 19. 3 by 12. That is 1 by 4. Next, 0 minus 0. 0 by 12. That is 0 itself. Next, 42 minus 32. 42 minus 24 plus 0. 42 minus 24. 42 minus 24. 18 by 12. 18 by 12. 3, 6, 3 2s. That is 3 by 2. Next, 30 minus 48. 30 minus 48. Minus 18 by 12. That is also minus 3 by 2. Next, 1 minus 8. 1 minus 8 minus 7 plus 19. Minus 7 plus 19, 12. 12 by 12, 1. This is the inverse of the given matrix by using Cayley-Hamilton theorem. This is the way to find the Cayley inverse by Cayley-Hamilton theorem. So, hence A inverse equal to 1 by 3, 0, 0, minus 5 by 12, 1 by 4, 0, 3 by 2, minus 3 by 2, 1. This is the inverse. This is the brief discussion about inverse of a matrix by Cayley-Hamilton theorem and the verification of Cayley-Hamilton theorem for square matrices. Is there any doubt in this concept? Anyone having doubt in this concept? Arti?
No, sir.
No, sir.
Sai Kumar? Do you
No,
have?
sir.
No, okay.
No, sir. No, sir.
Okay, okay. Next, we want to verify. We have to solve one more problem. That is, verify Cayley-Hamilton theorem for A equal to 3, 1, 1, minus 1, 5, minus 1, 1, minus 1, 3, and hence find A inverse and A power 4 by using Cayley-Hamilton theorem. Not directly A power 4, that is nothing but the characteristic equation. Now we want to find the characteristic equation first, then we have to verify this characteristic equation for the given square matrix. Then only we have to find the value of A inverse and A power 4. The characteristic equation of the given matrix capital A is determinant of A minus lambda I equal to 0. That is 3 by 3 determinant of 3 minus lambda 1, 1, minus 1, 5 minus lambda, minus 1, 1, minus 1, 3 minus lambda equal to 0. Now we want to expand this 3 by 3 determinant by using first row or first column, whatever. By using first row, we have to expanding this 3 minus lambda into 5 minus lambda into 3 minus lambda. 5 minus lambda into 3 minus lambda is 15 minus 8 lambda plus lambda square minus of minus 1 into minus 1. Vinila, what happened to you? Minus 1 minus of minus 1 into minus 3 plus lambda minus of minus 1, that is plus 1. Next plus 1 into minus of minus 1 plus 1 minus 5 plus lambda equal to 0. That is, simplifying this, we get lambda cube minus 11 lambda square plus 38 lambda minus 40 equal to 0, treating that as equation 1. Now we want to show that the given matrix satisfies equation 1. Who is this 25? Mute yourself. Neha. Okay. Now we want to verify the given square matrix satisfies equation 1 or not. For this, we want to show that a cube minus 11a square plus 38a minus 40 into I equal to 0. Let a equal to 3, 1, 1, minus 1, 5, minus 1, 1, minus 1, 3. Then a square equal to 3, 1, 1, minus 1, 5, minus 1, 1, minus 1, 3. 3, 1, 1, minus 1, 5, minus 1, 1, minus 1, 3. Multiplying these two matrices, we get 3 into 3, 9, 1 into minus 1, minus 1, 1 into 1, that is 9 itself. Next, 3 into 3, 1, plus 5 into 1, 3 into 1 plus 5 into 1, that is 8, minus 1, 7. Next, 3 into 1, minus 1, plus 3, that is 6 minus 1, 5. Next, by second row, all the elements of all the columns of second matrix, minus 1 into 3, minus 3, minus 5, minus 1, minus 3, minus 5, minus 1, minus 9. Next, minus 1 plus 25 plus 1 plus 25. Next, minus 1, minus 5, minus 3, minus 9. Next, with the third row, we have to multiply all the columns of the second matrix. 1, 3, 3 plus 1 plus 3, that is 7. Next, 1, minus 5, 1, minus 5, minus 3, minus 8 plus 1, minus 7. Next, 1 plus 1 plus 9, 11. So a square is 9, 7, 5, minus 9, 25, minus 9, 7, minus 7, and 11. Now, a cube equal to a into a square. That is, multiplying these two matrices, we get 3 into 9, 27, minus 9, plus 7, that is 25. Next 3 into 7, 1 into 25, 1 into minus 7, that is 39. Next 3 into 5, 1 into minus 9, plus 1 into 11, that is 17. Minus 1 into 9, plus 5 into minus 9, minus 1 into 7, that is minus 61. Next, minus 1 into 7, 5 into 25, minus 1 into minus 7, that is minus 120, plus 125. Next, minus 1 into 5, 5 into minus 9, minus 1 into 11, that is minus 61. Next, multiplying third row with all the columns of the second matrix, that is 1 into 9, minus 1 into minus 9, plus 3 into 7, that is 39. Next, 1 into 7, plus minus 1 into 25, plus 3 into minus 7, that is minus 39. Next, 1 into 5, minus 1 into plus minus 1 into minus 9, plus 3 into 11, that is 47. This is a cube. Now we want to substitute a cube, a square, a and I values in the characteristic equation, that is a cube minus 11a square plus 38a minus 20 minus 40 into I. We want to show that as a zero matrix. For this, substituting a cube minus 11 into a square plus 38 into a minus 40 into I. After getting simplified this, we get 0, 0, 0, 0, 0. All the entities of the matrix are zero values. That means that is a zero matrix. So a cube minus 11a square plus 38 into a minus 40 into I equal to a null matrix. Hence the given matrix satisfies the characteristic equation. Hence the Cayley-Hamilton theorem is verified. Now we want to take this equation as equation 2. Now we want to find A inverse from this equation. For that, we have to multiply this equation 2 with A inverse on both sides. We get A inverse into A cube minus 11a square plus 38 into A minus 40 into I equal to 0. A inverse into A square minus 11 into A inverse into A plus 38 into A inverse into A minus 40 into I into A inverse, or A inverse into I equal to 0. That means A inverse into A is always I, then A square minus 11A plus 38I minus 40 into A inverse equal to 0. Now 40 into A inverse equal to A square minus 11A plus 38I. Then A inverse equal to 1 by 40 into A square minus 11A plus 38 into I. Already we have A square, A and I values. Substituting those values in this equation, we get A inverse. A inverse equal to 1 by 40 into A square is 975 minus 9, 25 minus 9, 7 minus 9, 11, minus 11 into A, 311, minus 1, 5, minus 1, 1 minus 1, 3, plus 38 into 1, 0, 0, 0, 1, 0, 0, 0, 1. Now that is equal to 1 by 40 into 9 minus 33 plus 38. 9 minus 33 plus 38, that is 5. 5 plus 9, 14. 1 by 40 into 14. Next, 7 minus 11. 7 minus 11, that is minus 4. Next, 5 minus 11. minus 6. Minus plus 0 is nothing but minus 6. Next, minus 9 plus 11, 20. 20 plus 0, that is 20. Next, 25 minus 55, that is minus 30, plus 38, that is simply 8. Next, minus 9 plus 11, minus 9 plus 11, 2, 2 plus 0, that is 2. Next, 7 minus 11, 7 minus 11 minus 4 plus 0, that is minus 4. Next, minus 7 plus 11 plus 4 plus 0, that is 4. Next, 11 minus 33 plus 38. 11 plus 5, 16. This is 1 by 40 into 14 minus 4, 14 minus 4 minus 6, 20, 8, 2 minus 4, 4, 16. This is inverse of the given matrix by Cayley-Hamilton theorem. Next, we want to find the value of a power 4. For this, we want to multiply equation 2 with a on both sides. We get a into a cube minus 11a square plus 38 into a minus 40 into I equal to 0. That is a power 4 minus 11a cube plus 38a square minus 40 into a equal to 0. From this, we have to obtain a power 4 value. That is a power 4 equal to 11a cube minus 38 into a square plus 40 into a. 40 into a. Substituting a cube, a square and a values in this equation, we get a power 4 into 11 into a cube minus 38 into a square plus 40 into a. After simplifying these values, we get a power 4 equal to a power 4 equal to. Once again, you have to join. After completing this class, everyone should join another session, right? Please. A power 4 equal to 53, 203, 37, minus 369, 625, minus 369, 203, minus 203, 219. This is a power 4. Okay. Are you having any doubt in this problem? Is there any doubt to you, Mr. Sarath?
No.